This might be one of the most ambitious design and build projects I've ever attempted, and I'll be honest, it looks completely wacky. I mean, if you saw this without context, you'd probably think, what on earth is that supposed to do? But if this works, it could be one of the most important tools in the entire Project 250 journey. I've said from the beginning that I'm going to leave no stone unturned in my pursuit of speed, and this episode is exactly what that looks like in practice. At these kind of speeds, tyres are everything. If they hold together, you get a PB. If they fail, you can lose your car violently at 200 mph plus. And the problem is, up until now, most of my learning has come from trial and error on the car itself. That's expensive, it's time consuming, and it's not always repeatable. So the big question I asked myself was, how can I test tyres properly without destroying a whole set every time? The answer was to build a test rig that can replicate the forces, speeds and energy of a real speed run, but in a controlled environment. I set myself some very clear objectives. First, it needs to be able to test a wheel and tyre through the full operational envelope of a speed run. Second, it needs to generate real log data. At an absolute minimum, I want road speed and tyre RPM. And third, if possible, I want to measure tyre growth and temperature as well. If I can do all that, then this becomes a genuinely useful engineering tool. This entire rig is really about energy and force management. This is at the heart of RC speedrunning. I'm going to do my best to explain why. At the start of a speed run, you have energy stored in your batteries. To make your car move and to do your speed run, you have to transfer this electrical energy into two other types of energy. Firstly, kinetic energy. This is the movement energy of the car itself. And then there's heat energy, of which there's two parts. Aerodynamic drag, which is the energy of moving the air out of the way of the car and ultimately heating it up. And other losses like friction with the ground in the bearings, and also motor, speed control and wire heating. So all of those losses ultimately go into heat as well. I'm now going to talk about how much of this energy we transfer in a given time. This rate of transfer is power. The same power that boils your kettle or drives your car, measured in watts. I'm going to do a theoretical speed run on a graph showing the kinetic energy power and the aerodynamic drag power as the car's speed rises. The power going into kinetic energy builds up fast to start with. That's because at lower speeds you accelerate hard, and kinetic energy is related to speed squared. Then, as you go faster, aerodynamic drag picks up massively, since it's proportional to the cube of speed. The car then can't accelerate as fast, and the kinetic energy power drops down to zero, and all the power that your battery and motor can give at that speed is going into aerodynamic drag and losses. The car stops going faster. So that's what's going on in a speed run. Now, let's get back on track. If I'm going to have a chance of replicating that in my garage, I need to find a way of getting this energy out of the battery through the motor, wheel and tyre and into something. First things first, let's tackle the kinetic energy. Like I said in episode 1, my idea is to use the wheel to turn a roller. Like in these industrial test rigs, in fact they go back a long way. This one's from 1926. They must have been on something. That roller that gets turned by the motor and wheel, I'm going to carefully size it so that as it gets turned by the motor and wheel, the roller will have the same rotational kinetic energy as the linear kinetic energy of a quarter of the car at that speed. So that energy will have to be put into it by the motor, just like on a real speed run. The idea is simple in principle, car speed becomes roller speed, but the devil is absolutely in the detail. It was time to work this out. The inertia of the roller is critical, as well as its diameter, as that sets the RPM it'll spin at. So nothing fancy to start with, just solid cylinders in steel and aluminium. What became obvious very quickly is that the smaller diameter steel roller would be easier to do, mainly because of the cost. But there was a big issue. The smaller the roller, the further it is from a real flat road. The contact patch geometry just isn't representative. So the compromise was to increase the diameter, reducing its RPM and making its inertia too high, and then taking material off the sides of the roller to get the inertia back down again. I eventually settled on this. That felt like a good balance between realism, inertia, RPM and cost. Once I had the rough geometry locked in, I ran FEA in Onshape to check the stresses. I wanted to be absolutely sure this thing isn't going to turn into a grenade. This is where Onshape Professional really shines. CAD with integrated FEA and plenty of other useful tools like Render Studio, CAM and Advanced PDM. It goes without saying your data is 100% private. In case you didn't already know, Onshape is cloud-based, so it never crashes. The fact that it tracks all changes and never loses data is a genuine time saver. It's always the latest version and you can use it from anywhere and on any device. Personally, I've found it game-changing. Believe it or not, you can try Onshape Professional for 6 months for free. Use this link to sign up and see the light for yourself. The results were well within the material's capability. Things were looking good for this design. Now let's talk about the real world stuff that can make or break this rig. To drive the roller, the tyre needs to not just slip. I've been thinking about knurling the roller, bonding sandpaper to it and even an epoxy sand coating to try and match the rough surface of the runway at Clambedda. I'm going to be trying this coarse sandpaper first and go from there. After all, this is what they use on the industrial machines. At nearly 15,000 RPM, balance is critical. Any out of balance could give some horrendous vibration and maybe even cause the roller to come out of the rig. I'm going to try statically balancing the roller using my prop balancer to start with, and if that doesn't work I might have to get it dynamically balanced, which I'm not looking forward to paying for. In any case, I changed the roller design to make it easier, even though it doubled the cost. This topic absolutely blew up in the comments. Thanks so much for getting involved. So let me address the main suggestions. Why not use larger tyres? The physics actually supports that idea. Centrifugal force is inversely proportional to radius, so increasing the radius reduces the stress and gives you more foam to wear away. But there are trade-offs. I'm showing a truggy wheel here that I borrowed compared with a standard GT8 wheel. The truggy foams are incredibly hard to come by, whereas you can get the GT8s anywhere. And the truggy wheel has less offset. That means it'll stick out more from my motor, working against making the car narrow and potentially increasing drag. The wheel's taller as well, so it's definitely going to increase frontal area and drag. And because I'm direct drive, I can't gear around the larger diameter. I'll lose driving force. So for now, larger tyres aren't a free win. Rubber tyres came up a lot, as did urethane and fibre reinforced foam. There are some great ideas there. But foam tyres have a huge advantage. They absorb surface irregularities and small bumps, which gives you traction by keeping the tyre on the ground. I don't think solid rubber or even soft grades of urethane would do this. And the fibre reinforcement, because foams are made from sheets of neoprene foam rubber rather than moulded, I'd need to get the fibres added at source, and I can't find any suppliers offering this right now. So my approach is to start with the simple. Test what exists and then iterate from there, starting with modification rather than complete new design. Maybe later with that one. Like I mentioned earlier, energy gets lost to heat in the form of aerodynamic drag and losses. For the losses, my rig is going to have the same electrical components and bearings as the car, so I've got these covered. But aerodynamic drag? That's a whole different ballgame. From 200 to 250 miles per hour, the power needed to overcome drag doubles, so this is essential for the rig to be realistic. I explored a lot of options. Mechanical friction brakes actuated by weighted balls on ramps. Water braking, does water and electronics mix? Electromagnetic braking, basically using another motor as a brake, but could it vary the braking with RPM like the drag force? And even a Tesla turbine made from CDs, yes, I actually considered that. And then it clicked. A propeller. The beauty of this is that the drag power is proportional to RPM cubed, in the same way as it is proportional to car speed cubed. It's simple, cheap, adjustable by fitting different props, and backed by extensive data from APC. The downsides are noise, airflow and maybe safety. Now it's time to work out how all this goes together. I designed a rigid extrusion frame with chunky bearing blocks to hold everything safely. The wheel and motor are on a beam that pivots, and that pivot is aligned with the tyre contact patch to avoid jacking forces. I can then put weight on the beam to load up the tyre like in the car. I also decided to add a second motor to the roller shaft purely for speed logging, with that CAN network to the same vesc, so everything ends up in one data file. And then I had a brainwave. If I use a plain motor, I can mount the roller on one side of the motor and the propeller on the other side. Encoder, flywheel and drag device all in one. Some safety guards and a few other finishing touches later and the design was complete. Right now all of this exists on paper and in CAD. It obeys the laws of physics, but reality sometimes has other opinions. Next time this thing gets built, bolted to the garage floor, and we'll find out whether it actually works. Either way, I've got a feeling it's going to be spectacular. If you want to see tyres get shredded, make sure you're subscribed, and I'll see you in the next one.